Hi everyone. Yeah, just testing the sound. So today we're going to talk about TPS, which means transaction per second. And you might have heard about TPS quite a lot, especially if you go online, blog posts, and so on. But I'm going to try to take a scientific approach and share my thoughts about transaction per second. Okay, so I'm currently founder and CTO of Red Belly Network. It's a company based out of Sydney, Australia, and I also teach distributed systems at the University of Sydney. So you might have heard that blockchains are super fast, right? So you might be aware of that because you came across some documentation online, blog posts, or even news article. This is a document that is available on the Algorand website, and so there's the picture of Silvio Michele, and he explains that the plan for Algorand in 2021, and this is highlighted in yellow here, is that Algorand will achieve a transaction per second between 1,000 and 46,000 during the year of 2021. I guess this documentation was written before the end of 2021. So it gives you an idea of the performance that the blockchain is supposed to achieve. But on the other end, there's very little information about in which setting this performance result can be obtained. Another example is the one from Avalanche, which is another blockchain layer 1. And on their website, you can find the information that Avalanche can achieve 4,500 or even more transactions per second. Again, this is a blog post, I think, on their official website. But that doesn't indicate in which setting this performance can be achieved. And finally, Solana, which is known to be extremely fast, but leverages some particular functionalities like GPU and special intent instruction, is claimed to have achieved 200,000 transactions per second. And this was done in a test with 150 nodes. So you can see that the volume of transactions per second that is achieved is quite large. And there is some kind of competition between blockchain companies about which will get the higher number. And the problem that we have is that it's very hard to compare these claims, right? Because you don't know in which settings they were obtained, so it's very hard to say one is faster than another. Especially when you do research, what you try to do is to document your findings and make sure that this is reproducible. If you don't have the information, then you cannot reproduce this experience. So this summarizes just the metrics that I've just shown you, okay? What we observed, actually, we did some research, and it took us quite some time to evaluate the blockchain on the same ground, or to try to do so, was that actually our observed results were quite far from what was announced initially, right? So you can see the observed TPS. This is what we observed, and I will go into the detail on how we obtain these results later on. But you can see that it's significantly lower than what was announced. Right, so it was a big surprise for us, and we tried to go further and try to understand the reason of these discrepancies. So during this talk, I will just provide some few definitions. I will talk about the difference between the impression that someone has about the performance of blockchain and maybe the reality, what would happen if they use the blockchain technology in a real environment. I will then explain why, or give some hint about why we can have such differences before concluding and before talking about benchmarking. Okay, so I guess everyone is knowledgeable here about blockchain technology, but the idea is very simple. You have a client machine, or basically a wallet, that sends a transaction to a blockchain network. And then the responsibility of the blockchain network is to maintain the blockchain, which is a chain of blocks that you can see with the yellow block on the right-hand side. Now, the blockchain network has the responsibility to include this transaction into a block that will be appended to the chain. And the transaction per second is simply a unit of measure to capture the number of transactions per unit of time. Right? That's very simple. You can see the transaction per second as being the sending rate at which the wallet issues, or a set of wallets issue transaction to the blockchain network. But you can see also this unit to express the number of transactions that will be encapsulated in a block by the blockchain network. What would be interesting here, of course, you can imagine, is not really the sending rate. We're interested by the throughput, which is the output of the blockchain network. How fast can the blockchain network issue transactions per second, right? So we're not caring that much about a TPS, although you might guess that it has an impact on the throughput. We believe that there is another metric that is extremely important when you consider the throughput in transaction per second, and this metric is the latency. It's usually expressed in time, and it represents the difference between the time at which the transaction is committed or encapsulated in the blockchain, and the time at which it was issued. Right? It's just the difference between these two times. Why is it important to consider these two metrics together? Throughput in TPS and latency in time. The reason is that you can have a very high throughput because you're sending a lot of transactions per second and your blockchain network is able to encapsulate a lot of transactions very fast. But the problem is that if it takes you a day in order to respond to the wallet and says, yeah, your transaction is being encapsulated, then your service becomes not so interesting or not so useful for the wallet or the user, right? So it's always good to look at the latency and make sure that we're reaching a certain service level agreement. And for that guarantee, we have high throughput, right? That's even better. Okay, so let's talk about the impression versus the reality. Now we'll go back, of course, to the initial metrics that I've given for Algorand that I mentioned, Solana. This is an extract of a paper we have recently, we're about to publish it. It has been accepted for publication in the European System Conference next year. That will be in Rome, by the way, if you want to join. Anyway, you can see here on the left-hand side the performance of Algorand, Avalanche, Solana that I mentioned. If you look at the paper, you will have the references of these numbers. There is also a latency results, which is attached to each of these throughput in TPS that you can see on the third column. And the problem, again, was that we couldn't find the exact settings in which the results were obtained, right? So you can see at least that Solana uses 150 nodes, but we don't know much about what were these nodes, like what type of specification, how much resources they had in each of this machine. And then what we found out is that not only the throughput was quite different, but also the latency was much higher in our results than what was claimed. Now we'll talk about this setup in a minute. This is where we did our experimental, this is the experimental settings, this is where we did our experiments, in a testnet and in the data center. And I will explain why we choose this setup. It might not look very representative of a blockchain technology that needs to be deployed worldwide, right? When you use a data center setup. But it's actually where we can maximize the performance of these blockchains. Okay, so why so much difference? I won't give you a solution for that because I don't know exactly the experimental settings, but I think there are some reasons why the performance you obtain and what you think you can obtain are quite different. First, when we do blockchain experiments, we want to measure the performance. We're usually, it's often the case that we use synthetic workflows. So these are artificial workflows that do not represent the reality. For example, a payment system will typically not generate, a fixed transaction per second in sending rate. Right? It will depend on the demand at maybe the time of the day. So the synthetic workloads are often expressed in a fixed rate, and this is not realistic. The rate does not represent the variation. Typically, you might have some bursts at some point. This is not captured by the fixed rate. This hides the impact of congestion, for example. When you have a backlog of transactions that accumulates, this may translate into a huge impact in terms of memory usage that you underestimate when you use a fixed rate. So it is also better to evaluate throughput with latency, always together. The experimental setup has a huge impact on the performance result. For example, some networks are simulated, which means that we simulate the network by having, let's say, a simpler version of the network, which is not exactly a realistic network. Or we may emulate the network by introducing artificial delays, simply because we're doing some experiments with machines that are close by, but we would like to mimic what would be with a large latency over the world. The number of CPUs or cores that we're using will have a huge impact, as the amount of computational power you will be using in your network, the amount of memory, you mentioned it, for the backlog of transaction, might also have a huge impact. And finally, hardware optimization. So if you look at Solana, they were recommending to use GPUs, and I think they still recommend to use special Intel instruction if you want to run a node. So if you don't, so this, depending whether you have these instructions or not, you will not obtain the same performance. And finally, the distribution. Most blockchains do not scale well because they accept a constant number of transactions that is independent of the number of validators that you have in your network, or miners. They will typically have the miners composing blocks, but they will only accept one block out of many. So it doesn't really matter if you have 4 nodes or 1,000 nodes in your network. You will not get better performance with 1,000 nodes. Actually, you will create congestion, and you will exhaust the bandwidth that is available. So it's better to use in a small network. But of course, it wouldn't be really realistic if we were taking the smallest possible setting to evaluate the performance of a blockchain, right? We want to test it on large scale because this is what blockchain is supposed to do, especially in a permissionless environment. And there are rare blockchains that would combine purpose blocks into a super block. But it's the exception rather than the norm. Okay, so I'm going to talk about a benchmarking approach that we have taken in order to overcome some of these limitations that we have found. But before that, I just want to mention some of the interesting work that has been done by researchers and even developers online. There's this Hyperledger Caliper benchmark that allows you to test mostly Ethereum-compatible blockchains that would take, Solidity-based smart contract and then output the performance results. So it wouldn't apply to all the blockchain technologies, unfortunately. There is Blockbench that has been published at SIGCOMM, I think, in 2017, that features very interesting benchmarks in its framework. The YCSB, which is the Yahoo Cloud Service benchmark, that mimics the cloud applications, and the Small Bank benchmark that mimics the database. But unfortunately, it uses synthetic workloads and not real traces. Stellar has done a great piece of work Giuliano was part of. This was published at SOSP in 2019, and they did an evaluation of the Stellar network, as it was running. So they were focusing mostly on latencies, and they didn't provide a lot of capacity throughput result, because that was not the point of the paper. And Redmini, which is a blockchain out of Australia I'm working with, was evaluated worldwide using the Amazon Web Services platform. But the problem is that it was not compared against any other blockchain, so that was done in isolation. So we came up with this benchmark. It's called Diablo. It's a benchmark suite for blockchain technologies. So this is the paper I mentioned about that will be published in the European System Conference next year at Involve. And the interesting thing about that is we made the code completely open source, and we obtained some artifacts. These are just badges. They don't mean a lot for everyone, but for us it means that an artifact evaluation committee has taken our source code and tried to reproduce the experimental settings on the experiments themselves. They attested that the artifacts was available and functional. Unfortunately, they couldn't reproduce the experiments because the experiments that we talk about, they were done worldwide on 5 continents across 10 countries. It cost a lot of money. So these are the experiments where they were run. Each of these red dot indicate 20 machines that we deployed. Right? So you can see they're spread all over the world. We have one dot in Sydney. I guess you can guess the other location: Oregon, Ohio, Cape Town, Mumbai, and so on. So in total, we had 200 machines, right? Because 20 times 10 locations. And what we tried to do is to test blockchain in a realistic setting. So we used decentralized application. In particular, one was a mobility service with a real trace coming out of Uber, the Uber application. Of course, the trace is taken from the centralized Uber application, and we injected it on a decentralized version of this mobility service. We did the same for a web service where we took a trace of the FIFA website during the World Cup, a decentralized exchange where we used the NASDAQ trace, and a gaming application where we used the Dota 2 trace, one of the most popular game in Steam, and so on and so forth. And we decided to test 7 blockchains by, in terms of throughput and TPS and latency, while treating this realistic workload and running these decentralized applications. What we have decided to do is to try different experimental settings. As you can imagine, as I said, if you try to run on 4 nodes, you might have better performances for a non-scalable blockchain than across the globe. It makes sense. This is why we tested the data center setting, where we had only 10 machines. Each machine was quite powerful, 36 vCPUs, 72 gig of RAM, and only in the Ohio availability zone of Amazon Web Services. So it's like the same data center pretty much. So the bandwidth is quite high. We also did a test net, which is representative of what you could do as a developer of blockchain technology, right? You don't want to deploy it worldwide because it would cost a lot. You will just test your commit as part of a GitHub action in a test net, right? So you would do that on 10 machines maybe, using just 4 vCPUs, 8 gig of RAM, and a single data center. Then there is the DevNet environment, where we have 10 machines, but here we have the same machine as in the testnet, but because it's a DevNet, we would like to have partners evaluating their application on top of our blockchain. So we typically have machines spread all over the world in all the regions that I've mentioned before. Community, which is also with small machines spread all over the world, but here 200 machines, right? So 20 times 10. And consortium, where you can imagine that industry would team up together to provide machines that are well spread, but with higher resources than the community one. And this was used in a real network in the sense that we used Amazon Cloud Services, and we tested the ping latency that you can see in this heat map in red, and the bandwidth you can see in green on this heat map. Right? So this is expressed in megabit per second, and it represents the bandwidth that you have between any pair of regions all over the world. Well, this is the ping latency that you have between any pair of regions. So these are realistic. This is not a delay that is emulated, or it's not a network that is simulated. So we didn't use special hardware resources, right? We didn't use any GPUs or any fancy Intel instruction to assess the performance of our network. And we use a real network, as I mentioned before. The reason why in the early table that you've seen, Algorand was tested on the testnet, this is because this is where it maximized its performance in the testnet setting. Avalanche and Solana maximized their performance in the data center setting. So we tested on all these different settings, and this is where it maximized the performance. And here are the dApps that we have chosen. Again, these are very diverse, decentralized applications that we use for the experiment. They are quite different. You can see that the workload shape varies over time. For example, NASDAQ, when it opens in Wall Street in the morning, then there's a big burst of demand. This is what happened. That's why there's this big peak on the left-hand side of the NASDAQ demand. But again, this is the sending rate, right? It doesn't give you the throughput. Now, the mobility service has this kind of curve, which is compute intensive because it needs to capture the distance between any pair of drivers and users, right? So it's very CPU intensive. It computes the distance between them. The web service application, it's a counter that is heavily contended because it counts the request to the website. Gaming is at a very high sending rate, and YouTube, which is a video sharing application with the YouTube trace, that's even higher. Okay, so this gives you the characteristics of this decentralized application that we used in order to experiment the throughput in TPS of these blockchain technologies. Now, I just want to mention that the blockchains we have tested are also quite diverse, but they represent some of the modern blockchains that are quite popular these days. So Algorand, it uses a probabilistic, it offers some probabilistic guarantees, relies on the BA star consensus, and uses PyTIL as a binding language in order to comply to TIL. But we developed a smart contract in PyTIL because otherwise it's too low level. Avalanche is probabilistic, it has its own consensus algorithm, and is compatible with Solidity. Diem, deterministic, uses odd stuff, and the move language. So we had to implement this decentralized application in move, PyTIL, and Solidity. Quorum is deterministic, uses IPFT, Solidity. Redberry is deterministic, it uses DBFT and Solidity. Ethereum, as you know, it's eventual consistency. It's neither probabilistic nor deterministic, it's more eventual. In this particular example, we use the proof of authority consensus protocol, which is called CLIC, and it's compatible with Solidity. And finally, Solana, which is eventual consistency as well, in the sense that you need to wait for some confirmation before making sure the block will remain. It uses the Tower BFT consensus protocol and uses Solidity. So we did some performance comparison where we tested Algorand, Avalanche, Libra, that is now called Diem, Ethereum, Quorum, Solana, and Redberry. And we did two things, right? We captured the throughput and the latency. The latency is represented as a cumulative distribution function on the left-hand side, and the throughput is represented on the right-hand side. So this is some of these results are available in the technical report from one of my students, the And what is interesting here is that the CDF indicates, so not sure you're familiar with the cumulative distribution function of the latencies, but it essentially indicates a proportion of transactions, right? So if it reaches 1, it means 100% of the transaction. Now if you see, for example, that at like 20 seconds we have 100%, it means that 100% of the transaction took 20 seconds or less to be committed by the system, right? And so on and so forth, right? And what is striking here is that we were testing the NASDAQ application, which is a decentralized exchange dApp running the NASDAQ trace. Only one of the blockchain could commit all the transactions that we had. Like most of the blockchain will not even commit 80% of the transactions that were sent to the system. The rest were just lost, which means that the capacity or the demand was too high for the blockchain service to handle the workload, even though it's a realistic workload. And so that's why latency is super important when you talk about TPS. Now the TPS, doesn't mean much if you don't commit all the transactions. But anyway, we did the TPS over time with a window size, like a sliding window of 3 seconds in this graph. But what is important here is that you have a realistic application with a trace taken from a centralized application, injected in a distributed network, and this Web3 blockchain do not commit all the transactions just yet. We did another evaluation where we compared all these blockchains. And what we did is we took this 3 different decentralized applications. The decentralized exchange application is the NASDAQ trace. The mobility service decentralized application is the Uber trace. The web service is the FIFA trace. And what happened is here, instead of showing you the TPS, I decided to show you the relative speed up using Redberry blockchain as the baseline, right? Which means that if you have, so the Redberry performance indicated in blue here would reach 100% all the time. If a blockchain is faster, it commits more transactions per second, and Redberry would have a higher bar than 100. If it's slower, then it would have a lower bar than 100. Right? And this is the performance we obtain when we compare Redberry, Quorum, Algorand, Avalanche, Solana, Diem, and Ethereum. Here I have to mention that we had some issues, the Uber running on Algorand, where we couldn't commit any transaction, not because it couldn't handle the capacity, but there were other issues that are detailed in the paper. But overall, you can see that performance degrades. And most of these blockchains could not handle the workload that was sent to them. Even the Red network here achieves 100% of performance because this is the baseline in this example, but it could only commit 98% of the transaction for the FIFA workload. Fortunately, it could commit all the transaction for the exchange and the web service and the mobility service application. So to conclude, I would like to mention that the setup, the workload, and the distribution impact the performance greatly. It is important to document them as much as you can, as if you needed someone else to reproduce your experiments. Because when you do research in science, this is what you expect, right? People to be able to do exactly what you've done and get the same results. I would recommend for any person who is a blockchain developer to try to use a well-established benchmark to evaluate your blockchain. We tried to propose one benchmark that would provide decentralized application with those real traces, and it's called Diablo. You are welcome to use it. Again, it's open source. You can plug your blockchain. We have documentation for that. And you can also implement your own decentralized application if you believe that these ones are not realistic enough. So we would be happy to have your contribution on that. And again, if you can, try to compare with the existing blockchains. We try to make the experiment reproducible, but when you deploy on 200 machines across the globe, it's quite costly. The data set that we have used is publicly available as well, so you can just reproduce the same experiment on AWS with the same spec and compare with the existing results. And to conclude, if you're interested in this kind of topic, there is a MOOC online about blockchain scalability I've done with University of Sydney and Coursera, and there is the companion textbook that is published by Springer. Thank you for your attention, and I think we have a bit of time for questions. Yes.
If so, are you aware about their step function, and what's your thoughts on their step function?
Unfortunately, I'm not aware of step function. I know Era Ashgraf from an early white paper that I read. I didn't mention it here because I didn't want to go down the path of directed acyclic graph, which can provide much better scalability and performance that I've shown here. In particular for Avalanche, I think they use sub-networks, and I have to mention that I only use one network for these experiments.
Can I follow up?
Sure.
So Hedera, I'm a big advocate for, to give context, they also believe that they could scale infinitely, with step function and sharding, terms which even I'm trying to get my head around still. With your knowledge, do you think it's possible that a DLT or blockchain can scale to an infinite TPS?
I mean, you would need infinite resources, so probably not. But the idea is that if you shard, then you can, have a subset of transactions that are handled completely separately from another set. You just have to multiply the number of networks, then you will multiply the performance.
Thank you for the lovely talk. I remember you showed a chart with claimed latency and actual measured latency.
Yeah.
And you asked a question, why are they so different? And then I remember there was the rest of the talk. Could you sum up why are the numbers so different in a nutshell?
Yeah, so it's hard to say because we don't know the setup here, and we know that the setup impacts the performance, right? We have used this particular setup and obtained this performance. For Solana, typically we believe that they have used much higher performance resources than what we have used. In particular, at some point they were recommended to have GPUs and special intent instruction, things that we didn't use here, right? So maybe if you use these special machines, then you would have the performance that they have observed. Another thing to note is that Algorand, we talked to the team, so we contacted all the development team of all these blockchains and showed our results for them to try to explain. Algorand mentioned that the 1K TPS was obtained during a load test with a fixed rate in their, I guess it was a test net, I'm not sure. So it means that it's the peak throughput that they observed. Well, here, the performance I've shown you are average throughput over the entire execution.
Yeah, so you had that one visual with the, I think, 200 nodes set up across the various geographies. It looks like there are different classes of setup, because you have that test net, for example, and then I don't know what this maps to, but what's the, like, smallest unit, like a kind of micro benchmark type of configuration setting that has been tested against the benchmark? Right, the quickest thing to really just set up with some benchmarking against these other blockchains.
So we didn't use much of micro benchmarking in these things. Of course, we ended up having all sorts of issues that we had to fix by communicating with the teams themselves or finding ways around ourselves. The details are in the paper. I couldn't cover them here, but what I just want to explain is that when we say we just use one region, it means that we didn't use all the red dots. But when we use all, then we spread all the machines equally across all regions.
Got it. And those regions actually, I know Oregon is a big AWS data center. So those regions were tested in AWS environments? Like how were they deployed in those regions?
Yeah, so we use Ohio, Oregon, all these are availability zone on the Amazon Web Services, and we deploy the machines there.
Cool. Thank you.
Thank you. Yeah.
So regarding Algorand, and of course exciting news about the FIFA NFT collection being powered by the Algorand blockchain, I know they recently upgraded to a higher TPS, I can't remember now. In your professional opinion, do you think Algorand can handle the transactions incoming with the World Cup approaching?
At the moment, it's not the case. I think they have improved. Again, they have announced the results with a new upgrade that is more recent than the version we have used, and they achieved 6,000 TPS. I think. I don't think it's enough for the FIFA workload, for example, but we'll see. Thank you very much.